Let's review a little bit about Laplace transforms. Hopefully some of this material is familiar, but watching this video again may help you come back up to speed in case you're rusty on a few of the concepts. So most of the things that we can touch in this world can be described in terms of time-varying functions f of t. So for any value of t, usually greater than 0, for any value of t, we have a real number value that we can attach to that value f of t. So the Laplace transform is some operation that we perform on a time-varying signal. And then we usually denote the Laplace transform with a sort of fancy L in the curly brackets. So after we take the Laplace transform, we get some function capital F of s. So this is a very common denotation that we switch uppercase when we're talking in the Laplace domain and lowercase when we're talking in the time domain. That way we can use the same variable values, but we can realize without having to actually write the t or the s which particular domain we're talking about. So this is sort of a magical thing, right? We just magically get this function f of s, but what does s really mean? Well, we get s because we've created this integral, and actually this guy Laplace created this integral, and he told us, in a secret email from Superman's headquarters, that this was going to be really useful. So we integrate our function f of t against some complex exponential e to the minus st dt. So one way to think about this is that the result of this integration is going to tell us what are the most important moments of the time-varying function. That is, what's the frequency, real and imaginary, that this time-varying function responds to. And we're going to integrate, because we're talking about a signal, from 0 to infinity. We're actually going to replace infinity with some value b and take the limit as b approaches infinity. Because I seem to remember from like 100 years ago that this was important in a math class. So now, taking this limit allows us to talk about, with exponential decay, how important it is that this function responds to some kinds of inputs. Or how important is it at any particular time that we're going to have, for example, a spike in value. So we're integrating with respect to t, and we're letting t go to infinity. So let's do a little bit of this with a particular concrete example. So we have some function, f of t is equal to e to the minus at. So now we're going to substitute that in for f of t, and we're going to get the limit as b approaches 0 of our integral from 0 to b, e2, and here we can say minus s plus a t dt. So this particular integral is going to tell us, after we evaluate it, what is the Fourier transform of some time-varying function e to the minus at. So by the way, in case you forgot, the derivative of some e to the ax with respect to t, that's actually should be with respect to x. Let's fix that so we don't confuse anybody. With respect to x is a e to the ax. So if we have a value e to the ax, then the integration of that value is going, or some function e to the ax, then after we integrate that function, it's 1 over a e to the ax. And we get the same thing after we evaluate e to the minus s plus a of t. So remember, s, even though it's a variable at the end of integration, right now it's just some value, because it's not a function of t, it's a function of something else. So we can now write the limit as b approaches infinity of 1 over minus s plus a, e to the minus s plus a of t. And we're going to be substituting b for t and then 0 for t. So let's go ahead and follow through with this. So now the limit of b approaches infinity of this function minus 1 over minus s plus a, e to the minus s plus a times 0. So we substituted b in and went ahead and performed the subtraction. So not surprisingly, this value is going to go to 1, because e to the 0 is always 1. And when we substitute for b equal to infinity, this value is going to become 0. So a couple of negative signs subtract themselves away from each other, and we get this really simple result. The Laplace transform of a time-decaying exponential function with time constant a is 1 over s plus a. So let this sink in and think about it in terms of a particular moment. So if you have some function, e to the minus at, and the value a is clearly very important to this function, because that tells you basically how the system is decaying, how the value is going to be decaying. So that's actually a very simple way to describe this system, is all you need is this number a. A is the most important moment of the system. And so if you were to use a value of s equals to minus a, then you're going to get an infinite response, or an infinite value for the Laplace transforms. For the Laplace domain is going to give you an infinite value. So that tells you something about why that particular moment might make this system unstable. Relay this back to your ideas of physical systems, that every system has a moment, and if you're able to make it oscillate about that moment, then bad things will happen. So here, this tells you that if you can make the system oscillate with frequency minus a, then you're going to have bad things happen. Let's do another example. Now that we've done e to the minus at, some magical things are going to magically fall out. So here, let's consider that f of t is e to the minus j alpha of t. So remember that we can have imaginary values here. So e to the minus j alpha t is 1 over s plus j alpha. So we know that because e to the minus at is 1 over s plus a. So let's actually, because nature abhors a couple of things, it abhors a vacuum, and it abhors imaginary numbers in the denominator. So let's go ahead and multiply through by the conjugate. And we're going to get s minus j alpha over s squared minus quantity j alpha squared. When we multiply that out, we're going to get minus alpha squared. So we're going to get a plus sign in the bottom. So that gives us this actually easy to write, but not very pretty expression. But we'll see why that expression is interesting in just a moment. So in case you forgot, e to the jx for some function x is cosine of x plus j sine of x. So this is Euler's formula, and Euler's formula has also the cool value of Euler's identity. So if you use, instead of x of t, if you decide that you want x to just be a constant, you can choose e to the j pi plus 1 equals 0. So you can blow the mind of some philosophy major by talking about how adding imaginary numbers actually works, and they'll tell you something about Freud, I guess. Who knows? So that's how I always remember what this formula is, because you can substitute in pi and get sine of pi is 0 and cosine of pi is minus 1. So e to the minus j alpha of t is cosine of minus alpha t plus j sine of minus alpha t. And the cosine of a negative value is just the cosine of the value, and the sine of a negative value is the negative sine of that value. So now we have something that actually looks a little bit familiar. So we have some value minus j times some value. And this is a very interesting pattern here, because this allows us, without having to actually go through the integration of cosine and sine, to talk about what its Laplace transform is. So the Laplace transform of some cosine of alpha t is going to be s over s squared plus alpha squared. And the Laplace of sine of alpha t is alpha over s squared plus alpha squared. So we get those by looking at, again, just expressing the exponential as the sum of a cosine and a j sine. And we can set them, the left-hand side and the right-hand side, and break them down into their component parts. So that was a convenient way to avoid having to do a nasty integration of sine and cosine with some exponential involved. We can do a similar thing for setting a equal to 0. So e to the minus 0t is the Laplace, or so the Laplace of e to the minus 0t is just the Laplace of 1 over s plus 0, or 1 over s. So this actually gives us the step function. Another example. If we want to multiply exponentials times sinusoids, well, we can actually go ahead and write that sinusoid as exponentials. And then we can decompose those two pieces into a sum by multiplying through the e to the minus at. So now we have the Laplace of some exponential value over 2 plus another exponential value over 2. It's actually the conjugate. So let's decompose these a little bit more and go ahead and separate out the values as the sum of two Laplaces. So now we have e to the some value times t and e to the some value times t. And so we know how to take the Laplace transform of that. So this gives us 1/2 of 1 over s plus that value. So in the case of the first expression, a minus j omega is the value. In the case of the second expression, a plus j omega is the value. So, like we mentioned before, nature really doesn't like to see that j in the denominator. Let's multiply through by one another so that we can get rid of the j's on the bottom. We get rid of the j's on the top just by the fact that they're going to cancel one another out algebraically. And after we square the j omega squared, we're going to get that the Laplace of this value is s plus a over s plus a squared plus omega squared. So this is the Laplace transform of an exponential times a cosine. So you want to think about this as a decaying function that also is oscillating. So we're going to see these kinds of systems when we get done applying our inputs to the system. We may see that in the Laplace domain we have s plus some value over s plus some value squared plus omega squared. So by now being able to look at the Laplace domain, this is going to tell us how the system is decaying. So as an exercise for yourself, why don't you try showing the same thing for e to the minus at times sine of omega t. So go through this exercise to make sure that you understand how the math works.